Video 12. Holy crap, 12 videos. Are you guys having fun with these yet? Because I am having a blast, tell you what. Now, we're going to look at a special example, and we have looked at this type of example last chapter when we did confidence intervals that dealt with a matched pairs design. It kind of looks like, upon first glance, that we're dealing with two sets of data, when in fact these two sets of data are linked together. They form a matched, I don't know where that came from, a matched pair, because they are all related to, these two sets of data are related to the same subjects, the same people. So here is our example. And I need to change planes to plates because we were not looking at licensed planes. Police trainees were seated in a darkened room facing a projector screen. 10 different license plates were projected on the screen, one at a time for 5 seconds each, separated by 15-second intervals. After the last 15-second interval, the lights were turned on and then the cockroaches scampered, and the police trainees were asked to write down as many of the 10 license plate numbers as possible in any order at all. A random sample of 15 trainees who took this test was then given a week-long memory training course. They were then retested after the course, obviously. Test at the 5% significance level whether the memory course improved the ability of the trainees to correctly identify license plates. So, is this program a good program or not, is essentially what they're asking us. So here are all of our numbers out of, let's see, how many license plates did they do? They did 10 license plates, okay? And here is officers 1 through 15 and how many they could identify at the very end. So we had anywhere from, 4 is our smallest, 4 out of 10 correctly, all the way up to, hey, this dude remembered 8 out of 10, which is pretty decent. Then they gave him the week-long memory improving course, and then here's how many those same 15 could remember at that point. Now, for some people, they improved. Like this dude was at 5, and hey, he remembered an extra 3 after this program. The first person, you know, they could remember 6, and they still remember 6. So maybe it wasn't that great for him. Then we have some people like, hey, or 8. Maybe he just, you know, had a fluke, and now he only remembers 5. So was the training course, did it really make him dumber and not remember things? You know, maybe he had something good going on to begin with, and now this course just screwed him all up, and now he can't remember. So first we need to state our hypotheses, okay? So we're kind of dealing with two things here. We have our before data and our after data, and we want to subtract our data. And specifically, I wanted to subtract the after minus the before. And the reason for that is, if we think that the memory course really improves memory, then these numbers in this set of data should be bigger than the before numbers. Because we would hope that after the memory course, they should know more out of the 10 than they did before. Now, technically, you could subtract it the other way around, but I think it makes more sense to subtract the after and then the before, okay? So really this is saying there was no difference. The person remembered the same amount after from before. This plus 3 is saying that the person remembered 3 more license plates than they did beforehand. So here is the set of data that I'm really going to be using, okay? I'm not going to be using these 2 sets of data. I'm really going to be using this 1 set of data that involves differences, okay? So I'm going to call this mu sub d, or you might put diff, the mean difference. Now, if the program really had no influence on improving memory or not, then we would expect the mean differences to be 0. Okay? Or another way of looking at it here would be that the mean of the after should be the same as the mean of the before. Okay, it's another way of looking at it. Now, we might prefer to write it this way because now we only have 1 parameter. Here we have 2 parameters. So a lot of the times they will subtract these two and then call that subtraction just the difference. Okay. Now, alternatively, we want to hope to see that the difference is really going to be greater than 0. That the after numbers are going to be larger than the before numbers, so we should end up with a positive difference here. Or you could write that the mean of the after the training program should be greater than the mean before the program. You could write it either way, okay? Now, the main reason why you might want to write it this first way here is because, hey, we have numbers to work with. We have numbers in our hypothesis. Here, we don't necessarily see the numbers like we do here. So, well, first we need to also define our parameter. So, mu sub diff would be the mean difference in scores, and I'll say after minus before, in identifying, scoot some stuff, we'll just throw you away, in identifying license plates. So for our conditions, number 1, random. Do we have a random sample? And you know what? It does. It says specifically random sample of 15 trainees. I'm just going to leave it at that. Random sample of 15, check. We're good. The independent condition. Is the population at least 10 times our sample size? Or our population would be all trainees. And can we assume that is greater than 10 times our 15, which is 150? Do we think there's going to be more than 150 trainees? We will assume that that is true. I think it's pretty safe to say that there's going to be more than 150 police trainees. And then number 3, the normal condition, which again, since we're doing a mean level problem, is really a T condition here. Do we know that the population is approximately normal? We don't. Do we have a big enough sample size that we can use the central limit theorem? We do not. We only have a sample size of 15. So that means we need to look at a box plot of our data. And the box plot you want to look at is of your difference numbers, of these right here. Now, if you notice the way I kind of wrote stuff out here, I went ahead and put my before numbers into list 1, my after numbers into list 2, and then I went up to list 3 and I said, well, take L2 minus L1, and it did all the subtracting for me. Okay. Now, remember, I didn't want to do L1 minus L2 because I didn't want to see the before and then minus the after, which I'm hoping is bigger. If you did it that way, then most of these numbers would be negative and very few of them would be positive, in fact. Okay, but it's fine to do it that way. Okay, you're just going to be on a different side of your t distribution when we get there. Now, I already have the box plot set up right here. Now, based on this box plot, do we have any outliers? We don't. Is there any strong skewness? I wouldn't really think there is. Okay, so let me shrink this guy back up so I can get some writing room in here. So we will say, based on the box plot of our data, there is no outliers. There, I did it again, just like the last video. There are no outliers. There are no outliers, nor any strong skewness. So we may assume T procedures or a T distribution. You pick. Doesn't really matter as long as you mention that you may include T. And we're done. there's our part 1, part 2. Part 3, calculations. Now the calculations part for a matched pair looks exactly like it does as if we were doing a one-sided test here, which is this formula. Okay. Now the x bar, our sample mean, is really our sample mean of the differences. What is the mean of these numbers? That's what we really want to know here. So since I already have these numbers in list 3, then all I did was went to stat, over to calc, one variable statistics, and I used list 3. So here, this 1.53 repeating, that is the sample mean difference of my after minus before scores. So I'll just do 1.533 minus the hypothesized value. Well, my hypothesized value was that there was really going to be a 0 difference going on here. My sample standard deviation for the differences is 2.19. Well, let's see. If I went 4 sig figs on this, that would round to be 2.2, basically. So let's just do that, 2.2. All divided by the square root of n, and we had 15 in our sample size. Now, that should give me, let's find out here real quick. .699. There is my t statistic. So now if I draw a nice picture here, I am up above the mean, maybe, I don't know, we'll say right here. Here's t equals 2.699. My alternate hypothesis used the greater than sign, so I'm going to shade greater than. And now I need to find the area of that, which is my p-value. So now the probability that I find a t-score that is as extreme or more extreme than my 2.699 from my random sample of 15 trainees is equal to t-CDF. My lower bound is my 2.699. My upper bound goes to infinity, and my degrees of freedom, sample size minus 1, takes me to 14, which gives me a p-value of approximately, let's see here, t-CDF, I keep saying do-do. 0.008645. There is my p-value. Now, compare this. Is this truly less than an alpha value of 0.05? Yes, it is. We'll say check mark. Therefore, we may reject the null hypothesis. So our conclusion, we may say we do have enough evidence at the alpha equals 0.05 level to conclude. And there's a couple different ways you could write this concluding part, because the concluding part, again, always refers back to our alternate hypothesis. Now, you can write kind of exactly what it's saying here. We could say, to conclude, the mean difference after minus before of scores is greater than 0. Okay? Or what we could write is pretty much what we were trying to answer in this question initially, was, is the training program effective at helping officers remember license plates more? And it does, in fact. So you could also write, to conclude, the week-long memory training course does help improve one's memory. You can also write it that way, okay? Because that's basically saying the same thing here, just much more in context. And then we're done. Now, here is the problem that's in the book that you may read over. I know some of the text gets a little small, especially if you're trying to watch this on your phone. So you can pause the video, kind of read through this, and then here's some more, and some more. And then here's the problem that I want you to take a look at in class. If this is a little bit small for you, I know there's just a lot of data here to work with. Maybe you can zoom in with your phone, but if you're looking at it on your laptop or computer or whatever, hopefully this should be big enough that you can see what these values are. If you are having a tough time reading this, this is number 89, problem number 89 in your book. I don't know specifically what page it's on, but again, if you're having a tough time reading any of this, this is directly out of the book. So you could go look at problem 89, and please, 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 please try this problem out and bring your solution with you to class, and you can double check it because we will go over it together. Again, the only way you're going to get better at these problems is to practice, practice, practice. So please practice this problem, because you will probably see more questions like it in the near future. Hint, hint. Adios, we are done, finally, with all the videos of Chapter 9. On we move to Chapter 10, which will look very, very familiar. Goodbye until then.